Hi guys, carrying on video 3 in the series of particles. I talked to you about this slide and I hadn't managed to get this slide up, which was about impurities. If you want to pause the video and have a look at what I'm saying there, I simply was saying two things about how impurities affect the boiling and the melting temperatures. One, they make the boiling temperature go up and it becomes a range. Rather than one exact temperature, it boils over a range of temperatures. And two, the melting temperature goes down and again it will now melt over a range of temperatures. So I've done that as an example with water. Melting point in pure water 0 degrees Celsius. Melting point of salty water depends obviously how much salt is in there, but I've written something that's lower and a range, -5 to -2 degrees Celsius. How about the boiling temperatures? Well, water, instead of 100, it goes up. I've written between 102 and 104 degrees Celsius. Today's lesson though is more about evidence. What evidence is there that what we're telling you is correct? And you need to know in two ways that if we have some science and our work that we've done in science agrees with our world, then we should be able to find some things that happen in our world that are entirely consistent with our theory, if our theory is correct. If our theory is not correct, then when we look around the world, we will find a mismatch between the theory that says one thing and what we observe in the world, which is different. So doing this with this topic, we've been talking about particles. What evidence is there? Well, there's two kinds of evidence. One is observation in the real world, and the other is to look at experiments, scientific experiments that have been done, which talk about particles existing. This branch of science, across all the three sciences, is called kinetic theory, and obviously within the chemistry topic, we're using the word particles for now as a vague word before we get into what particles actually really are. So if I get into observations in the real world, what observations are there in our world that would point to these ideas I've been talking about as being correct? Well, the first one I'd like to talk about is drying. Like if these t-shirts were wet, they're wet because they've got water on them or in them, and what happens is when you dry them on a washing line is that the droplets of water, the particles of water which are on the t-shirts or in the t-shirts, the particles of water will jump out of the t-shirt into the air, and on a windy day they get carried away with the wind and become part of our air. But definitely the water particles are leaving the t-shirts, and when they've all left, then that t-shirt is dry. Putting it out on a sunny day with wind, they will dry faster. But keeping them inside, the same thing will happen. Particles of water will rise out of the t-shirt, go into whatever air is around them, and in that way the t-shirt will dry. That process is called evaporation. Water comes off the t-shirt by evaporation. It happens faster if it's warmer, but it still happens on a cold day. It does not happen just on a warm day. So evaporation is one of those things. that we can talk about. Evaporation the same way. Puddles. If you've got a little bit of water, say you spilled some water on a workbench, come back the next day, that small amount of water will have gone. It seems to have magically disappeared, but it's not magic, it's evaporation. The particles, if you can picture them in your mind's eye, puddle is made of lots of particles of water moving around each other slowly. Every now and again from the surface, one particle will leave the puddle, and then another one will leave the puddle, and other ones will leave the puddle from all over the surface of the puddle. As these particles are leaving, then that puddle will get smaller and smaller and smaller and smaller until all the particles have left, and then that puddle is no more. There is no more puddle. That bench will then be dry. The process, as I say, is called evaporation. Exactly the same thing happens with nowadays in COVID times. We wash our hands, and as we wash our hands they're wet. Even if you haven't dried them completely, when you go about your everyday life, you'll find that soon they dry. Well, that's because the small amount of wetness, the water particles on your hand, they will leave your hand, and when they've all left, then your hand is dry. So drying in its various guises is evidence that indeed water is made of particles, and those ideas that we presented to you are in fact correct. Well, I'd like to talk about another life experience, which is smells. And I used to talk about having a smell in a perfume bottle, or having a smell, a beautiful woman wearing a perfume as she came into the room, but I'm told nowadays that that is not PC, it's not to be talked about. So instead I talk about perfume that a person is wearing. So I want you to picture the perfume that a person is wearing. That situation, if the bottle has the lid on it, then you don't smell the perfume. It's because the particles of perfume are confined to the bottle, they cannot come out. But when you open the lid, then particles of perfume can shoot out of the bottle, or if somebody's wearing the perfume, the particles can come off their skin into the air, and when the particles of the perfume, which are smelly particles, are mixing with the particles in the air particles, the perfume particles, are rapidly, randomly moving around each other, then by that very nature of the movement, the particles will end up going to different places, and that is spreading out of that perfume smell. But for you individually, for you to smell that smell, the perfume particles have to go physically, they have to go up your nose. And they go up your nose, and then your brain thinks, ah yes, smell. So your brain will only recognise the smell if the particles we're talking about shoot up your nose. And that, all of that is entirely consistent with our ideas of particles that I've been whittering on about before. There are other smells though. So yeah, for example, me cooking. I like to cook, and my favourite food are curries, and when I'm cooking my curry in my kitchen, see, I'm not being sexist, because I cook the curries, not necessarily my wife cooking the curries. As I cook them, and if the window's open, then some of that fragrance, the particles of smell will go out of my window, and if my neighbour happens to be in his garden, they might end up through mixing, they might mix with the air, be carried through the air and go up my neighbour's nose, and then my neighbour will think, oh yeah, Ahmed's cooking that curry. So smells in their various guises are ideas of this existence of particles. And not a pleasant one is if somebody makes a smell and you don't smell it straight away, that's because those particles are not going up your nose. But as the spreading happens, as the diffusion takes place, and the particles end up in the air, and the moving air particles knock them around the room, eventually they might end up going up somebody's nose, and then that somebody thinks, oh God, what a horrible smell. And smells are consistent with our ideas in that way. So look, in my everyday experiences of drying and smells, I've been talking about spreading out. Well, there's a scientific word I want to introduce, and this definition I like because it's more a chemistry definition. I do not like the biology definitions that occasionally I come across with pupils saying diffusion is the movement of particles from a high concentration to a low concentration. I don't like that because it gives the image that particles are thinking. They're not thinking. They're not saying we're in a high concentration, let's move over there, which is a low concentration. They are just moving. And they're moving in all kinds of directions, and that movement in all directions will lead to spreading. So the diffusion definition which I want you to learn is the spreading out of gas and liquid particles. Solid particles do not diffuse. It's the spreading out of gas and liquid particles due to the motion, the movement of those particles is known as diffusion. And carrying on with what other evidence there is in the world, there are very common experiments that we do. So what experiments do you need to know about? Well, the experiments that we do are these three. Bromine in a gas jar, that shows diffusion in gases. Potassium manganate, which is purple crystals, put them in water, that shows diffusion in liquids. And the long tube experiment, which I'll talk about in a minute, which shows diffusion in gases, but it links the speed of diffusion to the density of the gas. So let's go over, and I hope that you've seen these, but this is a photograph of bromine in a gas jar experiment. You put a couple of drops of bromine in the very bottom. It's a red liquid. The red liquid quickly turns into a brown gas, and the brown gas is here. The brown gas is much more dense than air. If you put a second gas jar over the top that's full of air and leave it typically 10-15 minutes, then you find that that brown coloration spreads throughout both gas jars. And that shows you that the brown bromine particles are ending up spreading out even into the gas jar above, the air above, even though the density of them is much more than the density of air. The spreading out happens, and the only way that that can happen is if the particles of bromine are in fact moving, and they move for whatever reason, whether they're moving on their own or whether they're moving because the air is knocking them around. They're both valid ideas. What you need to know is because they end up at the gas jar that's above, then they have moved. There has been that movement, that spreading out, that diffusion has happened. And that shows diffusion in gases. That's one example, admittedly, it's just one example. It's just one piece of evidence. There are many other instances of gases diffusing in this way. Well, what about the second experiment? Crystals of potassium manganate. Potassium manganate is purple, and we put in a beaker. That's a beaker. I'm not sure you can see it very well, but that's a beaker. That's a stop clock. But beaker, potassium manganate in the very bottom, and this is a beaker with it's got some water in. You can see the top of the water there. So when normally we put some crystals through the water, you get some dissolving as they fall in. As they dissolve, that's that line you can see, the purple line. So potassium manganate crystals, when you see them, are intensely purple. And the purple colour starts off at the bottom, but you leave it, and at the end of a lesson, the purple colour has spread a bit. The whole beaker is not purple at the end of a lesson. We normally have to leave it about a week. We leave it about a week and come back a week later, then the purple colour has spread throughout the whole beaker. And that shows you diffusion in liquids. And just one experiment, but typical of so many liquids and they're spreading out. Why do we use potassium manganate? Because you can see it, you can see the spreading out. A bit like using bromine because it was brown, you could see it spreading out. This is purple, you can see it spreading out. This is diffusion. This is diffusion that you can see happening, but you've got to be patient, you've got to set it up now and come back in a week's time and take another look at it. Finally, we do this long tube experiment, as I call it, because this is the long tube. Over the years, our long tube has got shorter. When I first started teaching, it was like a metre long, and now I think the one we use is about 400 millimetres long. Anyway, you get some cotton wool, and you put some cotton wool into ammonia solution, which is an alkali, and you put some more cotton wool into concentrated hydrochloric acid, which is an acid, and then you put that cotton wool and that cotton wool together at the same time. You take them and you put them into the long tube experiment. It's crucial you do them both at the same time. As they go in to this tube that's got air inside it, then the hydrochloric acid will give off a gas called hydrogen chloride. The ammonia, the concentrated ammonia on that side, will give off a gas called ammonia. Ammonia travels this way, hydrogen chloride gas travels that way, and where they meet, they make a white mist. Now that white mist happens to materialize closer to the acid end. It materializes further from the ammonia end. So the ammonia has traveled all that distance in the same time that the hydrogen chloride gas has traveled a shorter distance. And the density of hydrogen chloride is much, much more than the density of ammonia. So the ammonia density is less, and look, it travels much further. So not only does this show diffusion because the two gases meet, it shows that low density gases, that's light gases, although light is not a good term to use, low density gases, well, they diffuse much faster than higher density gases. The hydrogen chloride is much higher density than ammonia. So that's diffusion in a long tube experiment. If I told you about what they ask about most, it's this one. It's this long tube experiment that examining bodies at GCSE ask about most. The white solid, the white mist that's made here is ammonium chloride. Now later, as the course develops, I'm hoping you can write an equation for that reaction that gives that white mist. Ammonia plus hydrogen chloride gas makes ammonium chloride, which is a solid, and it's a white solid. So these experiments tell you that indeed the world is made of particles, and that diffusion is a scientific process that I want you to know about. I want you to learn the definition for diffusion, and I think that third video brings the end of the particles topic. So next time I'm going to talk about, I think, elements. We'll talk about what are the nature of the particles, and try and build you up to understanding what particles are later. So elements next time. See you then. See you guys.